Just one of you, is this your only class today? A lot of you? Yeah? No? Yes? Half of you? I'm impressed. Thank you for showing up today. Okay. We're going to continue through Moore's circle. All right, just do a bunch more examples showing you how you can relate stress states at a known orientation and figure out what's the maximum normal stresses and shear stresses and what orientation do we need to look at, like what angle do we need to cut our material at to see those max stresses, right? Both for shear stresses and for normal stresses. And so we're going to jump through some of those today, or continue to jump through some of those today. So we started an example where we were just looking at a simple axially loaded bar, right? And we calculated, well, what's the max stress in this? Well, we know the max stress is going to be at a plane that's perpendicular to the applied load, which is just an axial load, right? So we calculated our maximum normal stress. Then we decided, okay, we're going to go back and we're going to look at it through the axial chapter, right? We derived a couple equations for figuring out, well, what is the axial stress and the shear stress, right? Knowing that as we cut this axially loaded bar, right, when we start looking at angles other than perpendicular, we get these two components of that resultant force, right? The resultant P. So we end up getting a normal force and a shear force, right? That was all of this stuff, right? P stays the same, right? And so when we start cutting this at other angles that vary from perpendicular, we end up with these two components. We get an N and a V. And because we have N and V, we know from our original, right, derivation of stress, both shear stress and normal stress, right, we're going to get a stress over those areas based on the magnitudes of our normal force and our shear force. Okay, so we calculated what those were based on those equations, and we figured out some magnitudes of stresses, right, and directions. And then now we started diving into, well, what does this look like if we wanted to look at Moore's circle, right? Because it's great if we wanted to go through and figure out the angle or the stresses that are acting at a given angle. In this case, they asked us for 57 degrees. Well, what if they asked us what the maximum stress was, right? If we use this approach, it'd be really hard. You'd have to go through and pick all the different angles and see, the magnitudes of our sigma x and sigma y and our tau x, y's. And then we'd calculate, okay, after we calculated every single angle, we'd go back through and we'd figure out what the maximum was, right? So that's where the power of Moore's circle comes in, is that once we know our initial stress state, right, we can plot our 2 points. And so that's what we did, right? We have an orientation for our stress block. In this case, that orientation is aligned, okay, with our x-axis. We put an axis along the length of our bar, okay? Our block is aligned with that, and we know with that orientation what the stresses are on all four sides of our stress block, right? Look just like this. We have zero shear stress on the x and y faces. We have zero normal stress on the y face, right? There's no forces acting vertically trying to tear this bar apart, right, in the vertical sense. So all we really had was that normal stress in the x. And so we get two coordinate points, right? The coordinates that we plot in our Moore's circle are the shear stress and normal stress acting on the x and y faces, right? So we have 2 points on the x face and 2 points on the y face, okay? Our x coordinate is stress in the normal direction, and our y coordinate is stress in the shear direction, right? So in our case, because we had zero shear stress, we ended up with these 2 points that were 150 megapascals and 0, and then 0, 0. We ended up at the origin, right? And these points could be all over the place, right? It's just what the stress state is that you derive at a given orientation. We're going to do a bunch more examples here, okay? So then from those 2 points, I can draw a circle, right? We know that this circle is always going to be centered on our x-axis, right? Because shear stress, we know, is equal and opposite. So for every point above the curve, we're going to have a point equal and opposite across the curve, right? Above and below, and then continued across the entire circle. So we got this nice circle. We plotted our 2 points. And they asked us for, well, what's the stress state at our 57 degrees, right? 57 degrees. Well, we know in Moore's circle that everything that's in Moore's circle is twice as much as what's happening in the real world, right? Theta, which is our real world orientation, okay, is half alpha, which is our orientation on Moore's circle, where alpha is 2 times theta. So in this case, right, they asked us, part 2, they wanted theta at 57 degrees. They asked us, well, what's the stress state at an angle of 57 degrees? What's going on a plane or a surface that's at 57 degrees? Well, in our case, what does that mean? Well, that means we need to look at an alpha at 2 times theta, or 114 degrees. Right? So we know we're going to do 114 degrees. So what does that mean? Well, that means that we're going to take our x face, right? We're going to take this orientation here, right? Say we were looking at 1, and we're going to rotate it up to this 57 degrees. So that was our x face, and now this was our x face, right? So we're just going to rotate it counterclockwise, and we're going to figure out what's going on that surface at 57 degrees. And so what do we do here? Well, that means we take our 2 points. We know that this is our x coordinate on the right-hand side, like we showed in the thing. We wanted to go in the diagram, right? We want to go 57 degrees. So in here, we need to go 114 degrees, right? We're going to just rotate about the center, 114 degrees. So we're going to grab the center. We're going to rotate. Alpha, right? That's the angle that we rotate. And so those 2 points now on the circle are going to be the stress states on the x and y face, right? This point was the x face. When we rotate this angle 114 degrees, now this is our x face stresses, right? Normal stress and shear stress. Similarly, our y face, it goes from our origin in this problem, and it's going to rotate 114 degrees. And this point out here on the circle is going to be its stress. Well, in order to figure out those points, right, we want to use trigonometry here. We're going to just look at some triangles to figure out the magnitudes of those 2 locations, or the coordinates of those 2 locations. And so in order to do that, we need to know what's the center point, right? C. That's going to be very helpful. That essentially establishes the pivot point for this circle that we have. Well, as I mentioned before, that's really just our average stress, or I'm going to say it's sigma x plus sigma y over 2. In this case, sigma x was 150. Sigma y happened to be 0. We're going to divide that by 2. We get a center equal to 75 megapascals. Okay? So what does that mean? Well, that means right? And our center's always going to be on this x-axis, right? It's always going to be on this axis because our shear stress is always equal and opposite. So the center is always on the x-axis. So the coordinates of our center is always what we calculate for C, right? 75, comma 0, right? Because it has 0 shear stress and it has a normal stress magnitude of 75 megapascals, right? It's positive. What does that mean? Well, that means it's in tension, right? We're on the right-hand side of the y-axis. And you can visually see that, right? On the right-hand side, 75 megapascals. Another big component here, right? If we're going to use trigonometry, we're going to need to know magnitudes, right? Or really the components of this triangle that we can generate above and below. Right, if we look at this, right, we kind of have these 2 triangles that are acting, right? So out of these 2 triangles, we really want to know the hypotenuse or the radius of this circle, right? So we can use an equation to figure out the radius. We're going to use Pythagorean's theorem here. We're going to say it's sigma x minus the center squared plus tau xy squared. Or the radius is the square root of sigma x minus sigma y all over 2 squared plus tau xy squared. So we got a couple options here, right? Basically, it's the same equation, okay? Just in two different forms. So what are we trying to find? Well, we're trying to find essentially what those components of those of that triangle, so that we can find the hypotenuse, right? Tau xy is going to be 0 in our case, right? So I'm finding the radius based on our initial known points, right? X and y faces. In this case, the coordinates of these are 150, 0, and 0, 0. So what does that mean? Well, that means our shear stress is 0, right? We're on this x-axis. And so then when we go to calculate our radius, it just becomes our sigma x, right? That was 150, minus the center, where we calculated that as 75, right? That's just, honestly, just the distance between these 2 points, right? We're gonna square it, and then you're gonna take the square root of it, right? So essentially, we don't have a triangle here. If these 2 points happen to be where our black dots were, right? We would then have to figure out what those components were. In this case, it's pretty easy because it's just sitting on the x-axis. So we get 75 megapascals. That is the radius of our circle. So now if we start looking at, okay, now that we know r, right? We know the radius. Well, now we can figure out, okay, what are the coordinates of our 2 points, right? Our x and our y faces. Well, if we look at sigma x, it's going to be the center minus the radius times the cosine of alpha. Right? Radius minus the cosine times, radius times the cosine of alpha, right? The center minus that, right? Because we're figuring out what's our normal stress, right? We're trying to figure out our x coordinate. And so we're going to start with our coordinate of our center, and then we're going to subtract from that the cosine of alpha, right, times the radius, which is essentially just the horizontal component there.
Isn't the sigma x the 150?
Yeah, but so now we're trying to figure out this new sigma x at 57 degrees. So we're trying to figure out our black point up there. Yep. So we're trying to figure out x. Right? This is our x coordinate, right, of our x location. So we've got sigma x is c minus r cosine of alpha. Well, that's 75 minus 75 cosine of 114. That equals 44.5 megapascals. Now, if we look at sigma y, right? This is our y face. We got c plus the radius times the cosine of alpha, right? So now we have the center point. We want to know the x coordinate of this point here. Well, it's going to be the center point plus the horizontal component of our radius, right? That's kicking us off to the right. Pretty straightforward. Go through that same thing. 75 plus 75 cosine 114. We end up with 105.5 megapascals. And lastly, we have shear stress, right? Our coordinates, these two black points, right, are above and below the x-axis, so they have magnitude on the y-axis. And so we can figure out what those are. We're going to say that our tau xy now is really just the R sine of alpha, right? Or 75 times the sine of 114, which gives us 68.5 megapascals. Right? So what does that mean? Well, if we looked at a block, a new block, we would have sigma x and sigma y. Well, as we can see here, both of these are positive, right? So they're both in tension. We're on the right-hand side of our y-axis. So our sigma x, sigma y, we know sigma y is 105.5 megapascals. Sigma x is 44.5 megapascals. And then we have tau xy, right? Well, if we look on the x face, which is our x point there, we're above the x-axis, right? We're above the x-axis. We have a clockwise shear stress on that face. So on the x face, it should be acting downward, right? It's going to try and spin this block clockwise on our x faces. So similarly, we know we got equal and opposite on our y face, and that is equal to 68.5 megapascals, right? Well, if we look right here, sigma x, 44.5 megapascals, sigma y, 105.5 megapascals, tau xy, 68.5. In this case, we got the magnitude out of it, negative, which meant that it was, right, spinning on the positive x face, it was acting in the negative direction, negative y face, acting in the positive direction, right? These are negative shear stresses. And as you can see, our stress block looks the exact same thing, right? So we can get the exact same thing with Moore's circle. The benefit of Moore's circle now is instead of having to look and see, okay, well, what is the maximum stress state for our block or our material? Well, we have our principal stresses, right? And we have our shear stresses. Well, our principal stresses we came up with them originally in our known stress state, right? Those are sigma 1, which is our maximum normal stress, sigma 2, our minimum, which would be 150 and 0. And then our maximum shear stress, right? Our material is going to have an allowable shear stress in it. Well, our maximum shear stress is really just the top and bottom of our circle, which is just the radius, right? So our maximum shear stress would be 75 megapascals, and we could do that. Yeah?
Can you go over again? Oh.
No. Yes, I can. Of course I can.
How you got that it's a negative, the twist?
The negative twist? Yeah, for sure.
Because I get it when you do it.
Here, when it comes out as negative.
Yeah.
So if we go back to right here and figure out and just review the sign convention a little bit, right? So when we put a coordinate axes on a block, we've got an x coordinate and a y coordinate, right? And that x coordinate and y coordinate denote whether we're on the positive face of the block or the negative face of the block, and if the shear stress is acting in the positive direction or the negative direction, right? So on this block, if our shear stress is positive, that means that the shear stress is on the positive face and it's acting in the positive direction, right? Or the negative face and acting in the negative direction, right? And then similarly on the top and bottom, right? Positive face, positive direction. So we got a sign convention for this, which we followed in the example when we calculated the actual shear stress, right, being negative. So we knew based on that our shear stresses were going to face in this direction, right? Positive x face, the shear stress is acting in the negative direction. It's a negative shear stress. And we could establish all four of these, right? Really knowing this one, we know what the rest of them are. When we go and use Moore's circle, the way that we use Moore's circle to figure out the direction is the coordinates based on our Moore's circle is that our y-axis, our shear stress is positive in the downward direction, okay? and the downward direction for our shear stress axes is counterclockwise. So any point that's down here is going to try and spin our block counterclockwise. Any point that we have up here is going to try and spin our block clockwise. Okay? So that's how you establish the directions. Which, if you use that convention with Moore's circle, right, our X face should be spinning our block clockwise. Which, if we look at our X faces, right, I guess I put coordinates on this for you. Okay, X and Y. So on the X face, these two forces are trying to spin clockwise, right? These two forces, because now our Y point is on the bottom, right below our X axis, is trying to spin it clockwise, or counterclockwise, sorry. Oh, why didn't you, look at that. Huh? Is that what you were trying to get at that whole time? You're just waiting for me to figure that out? Huh? So that should be right, okay? This is spinning it counterclockwise. Does that help you out there?
Yeah.
Okay, sweet. Yeah.
On the circle, when you have the X and Y points, how do you determine which ones you're gonna call X?
Because it's based on starting with the original points that you established, right? So when we established our original points, those two blue points, right? I essentially said that this is my X coordinate, right? This is my X face. And so when we came up with our stress block, that means that this stress is the X stress, right? So now when we plotted those points, right? Even though there's no other forces here, we could still say that we could do this. If I can get them all in the right direction. We said sigma y, well that equals 0. Tau xy equals 0, right? So we really have 4 points on this block, or 2 coordinates. We have a coordinate that we can use on the X face, and a coordinate we could use on the Y face. And that was all based on the known point, right? A known stress state, okay? And then from there, we plotted those points on Moore's circle. Right? Those are those 2 blue points. And because we established the axes down the length of our bar as the x-axis, this point is our x-face coordinate, right? We have 150 and we have 0. Okay? And then similarly, the other point that we plot is the top and bottom of our block, and that is the y-coordinate. So that's right here. What they asked us for was, what is the stresses at 57 degrees, right? Rotated 57 degrees. And if we look back here, we're going to start with a block that's oriented with the bar, right? And they said we want to go to 57 degrees. So I took the X face and I rotated up and I said, okay, we have 57 degrees, right? So we're rotating from an axis that's along the length and we're rotating it up 57 degrees. So now this face is our X face. Right? And because I rotated counterclockwise, right, I just take my Moore's circle line that connects my 2 known points, and I do that same rotation, right? We went from a horizontal orientation, right, the 2 known points, and we rotated, right, at this point we rotate alpha, which is twice theta. We rotate 114 degrees, and that's how we establish that. So X point really just traveled along the circle, 114 degrees, that we got right there. Does that help you out? Okay. Any other questions? Questions are good. This is a safe space. Yeah. Doesn't matter.
When you take, when you do the radius times the cosine of alpha, I'm just like having trouble visualizing what.
So it's just trigonometry at that point. So like you essentially get the same answer when it's 90 minus something. So you'd get the same answers if you looked at it. If you looked at it versus this angle. Is that what you're trying to get at? It's like, why did we do that versus just using that angle? We could have, you'd get the exact same answer.
Okay.
You'd get the exact same
So I
answer.
guess you like the green, like horizontal.
Yep, you would get this green horizontal. So it's the fact that, sorry, not 90 minus, but 180 minus that is the exact same thing. Any other question? You could use the inner angle. You could say 180 minus 114, and then you could go through that, right? 76 or whatever it is. Yeah.
To find the radius, do you need to do that equation, or can you just look at it?
You could totally look at it. You could totally look at it. But it's not always as simple as the 2 points that you establish are going to be along this x-axis. We're going to do another example where when you start with a known stress state that has shear stresses in it, now you're up here and down here, right, with your initial points. And when you're up here and down here, it's just nicer to do it. But you can totally, I mean, it's essentially just finding the hypotenuse of a triangle, right? And that's the beauty of the Morse circle, and that's why I try and teach it this way, is because even for me, I mean, in the practicing industry, I have used this where I plot points and figure out what our principal stresses are, because it's easy to see it, okay? Instead of blindly using, there's equations out there, okay, that you could just plug in and it should give you sigma 1 and sigma 2. It should give you maximum shear stresses, right? But yeah, you can visually look at it, you make a triangle and figure it out with geometry. Anything else? Okay, we're going to do another one where we start with a little bit more complicated initial stress state, right? Because that's the whole a big part of this is the fact that we need to calculate what's going on with a stress block at a known orientation, right? So we need to be able to figure out what's going on at a point. And that's what we've done up to now with respect to torsion and axial loads, right? So we've got a torque that's applied to the shaft that's hooked up or fixed to the end to the wall, for instance, okay? And then it's got an axial load pulling it out of the wall, right? So we've got a T and a P, right? They're giving us what T and P are. We've got 30 kilonewtons for our axial load and 100 newton meters for our torque. And they want us to populate a stress element. That stress element is this little block H, right? Oriented along the axis. So the X face of this block is along the x-axis or perpendicular to the x-axis, right? And then they want us to illustrate Morse circle and determine our principal stresses and our maximum shear stress, right? Which is really what you would do in the real world if you were analyzing something, right? And you're doing analyzing something outside of like SolidWorks, right? In SolidWorks, you just model it and you'd say, give me the maximum principal stresses, and it's going to give them to you, okay? But if you're doing something simple and you want to do it by hand, right, this is the method you would use. So, what's the first thing we need to do here? Well, we need to populate a stress element. So we've got this little stress element, right? It's oriented along a plane, right? That's cut perpendicular through this solid shaft, right? We're going to need a few more things out of here to populate this stress element, right? Stresses are a function of our cross-sectional areas, our polar moment of inertia, those types of things. So if we go back and we say, okay, if we have an axial load, we're going to have an axial stress, right? And if we have an axial stress, we know that stress is force over area. I'm going to say that our diameter equals 20 millimeters. Okay, right, that's up here, 20 millimeter diameter shaft. Our diameter is 20 millimeters. Well, we can figure out our area. We know P is 30 kilonewtons. Our area is pi over 4 d squared, or pi over 4 times 20 squared, or 314.16 millimeters squared. It's probably way more digits than I need, okay? So our stress then becomes, right, 30,000, I'm gonna call it newtons, because I'm gonna get newtons per millimeter squared, right? 314.16 millimeters squared. That gets us a stress of 95.5 megapascals. It's positive, right? Our force is positive. It's acting outward normal. We know that for normal stress, our sign convention is positive is in tension, negative is in compression, right? Or towards or away from the surface. Well, in this case, P is acting away from the surface. We get a positive normal stress. We get a tension on our rod. Shear stress. TC over J, right? You guys are dealing with that a lot now. Homework was due yesterday. You got to play with that a little bit in the homework. In this case, our torque is 100 Newton meters. C, well, that's our maximum radius, right? To the outside face of our shaft, or 20 over 2, or 10 millimeters. And J, well, J, as we know, I gave you all the equations for the polar moment of inertia for both a pipe and a solid shaft. Well, it's pi over 32 d to the fourth, or in this case, 15,708 millimeters to the fourth. So we can figure out the shear stress in this bar based on, so we will have 100 Newton meters. I'm going to convert that to millimeters, so 1,000 millimeters per meter. 10 millimeters is our maximum radius, and our J, we said, was 15,708 millimeters to the fourth. We end up with newtons per millimeter squared, and the magnitude is 63.7 megapascals, right? And as you can imagine, if you do this part wrong, your Morse circle's wrong, right? So there's a critical point in this, is that you need to calculate your normal stress and your shear stresses correctly, right? So in this case, we have torque, we have the max radius, we have the polar moment of inertia, we can figure out the shear stress, right? And as we know, if we look at this shaft, at cross section, right? Looks something like that. Got a circle. We got this overall torque. And if we were looking down on the end of this, that torque is going to try and twist this shaft counterclockwise. Well, we know from earlier in the class with our derivations of shear stress, right? The shear stress is going to be in the direction of that applied torque. So it's going to be doing something like this to 0. Right, where we have 0 shear stress at the centroid of this cross section, or the center of this cross section, right? That's where our C effectively, right here, TC over J. C is 0. Well, C is 0, our shear stress is 0. That's why the maximum shear stress is maximum at the maximum radius, or out here on the edges of this, of our shaft here. So it's our shear stress is maximum. So if we were looking at point H there, right, it's on the left-hand side. Our point H is really right here. Okay. If we drew a stress block of that point, do something like this. Stress block, this is point H, right? On the right-hand side of that stress block, that stress is going to be acting downward, right? Because that torque is going to be trying to push that material down. It's rotating downward. So on the left-hand side, we have a downward stress. It looks something like this. Because of that, we know all the other stresses that are going on all 4 sides with respect to shear stress, right? And we know the magnitude of that shear stress. That was 63.7 megapascals. If we look at normal stress, well, if we look at the edge of that H block, right, we've got no stress on the Y face. There's nothing going around the circumference, okay? And so that P force is just trying to pull that little stress block apart, right, horizontally along the x-axis, right? If we put a coordinate in here, this is x, this is y. Sigma y equals 0, so we don't have that. And sigma x, we know is 95.5 megapascals. So that's our stress block. Okay. When they say to populate a stress element, that is what they're talking about. Yeah, Drew?
I think you've probably described this a million times already, but
Probably.
the shear stress arrows.
Yeah.
I know we're not going the other way again.
In this case, if we were to look at this stress block H, right? It's on a cross section. Right? If we were to cut this off, that would show us the right-hand side of this stress block. Okay. We know that if you looked on the end of this shaft, this torque is trying to twist it counterclockwise, right? Trying to twist downward. And if it's twisting downward, right, our shear stress is going to be downward on this left-hand side, right? And because it's up downward on the left-hand side, then if we were to cut this shaft right here, right, and remove all the end material, this torque is still acting right here, right? The torque acts all the way down until it gets taken out at the end. And so you end up with a stress that's acting downward on the right-hand side of this block. Does that make sense? So then we can establish what's going on the right-hand side. And the second I draw one of these arrows, I know the rest of them, right? It has to be in equilibrium. So on the right-hand side, it's down. On the left-hand side, it's up. And then it's got to be equal and opposite in the other direction, right? Because these two are trying to twist this block this way. Well, these two have to twist that block backwards. Yes?
If you were to cut on the left side of the block, wouldn't that be opposite?
Yes, it would be, if I were to cut it on the left-hand side?
Yeah.
Yes, because if we cut it right on the left-hand side, right? If we cut it, let's just draw it. So if we cut it on the left-hand side, right? And now this is H, right? Or I guess let's put a little gap here. So we have H sitting right there, right? Well, if we look at our applied forces, this is our x coordinate. If we look at our applied forces, we've got a torque acting on that end, right? Clock or counterclockwise. It's really a double vector arrow pointed that way. Well, for this to be in equilibrium, we're gonna have to have an equal and opposite torque acting the other way on that same block, right? If we were to cut this out. So really, on this side, that torque switches direction, right? In order to make sure that that block stays put. And so if it torques and it's twisting the other direction, now the stress that it's putting at H is actually upward. And so then we would get the upward stress on the other side. Any other questions? No? I'll get rid of that. Okay. So that's our stress state, right? That's what we know. We know that based on our applied loads and this stress block that's oriented, right, along the axis of our member. Well, now they asked us to populate a Mohr's circle so that we can review, well, what is, because of this known loading, right, and this known stress state, what's the maximum normal stresses, what's the maximum shear stresses, or what are our principal stresses, and what are our max shear stresses? So we need to draw a Mohr's circle, right? So if we draw so beautiful. Man, so nice. It would look like shit otherwise. Yeah. Oh, you raising your hand or just stretching?
Yeah, I was gonna ask, like on the shaft question, will there ever be a signal Y?
Nope. Nope, until pressure vessels. But the rate that we're going through this class, I don't know that we're gonna go through pressure vessels. Yeah. But pressure vessels are cool, right? Like pipes, okay? Anyone seen a burst pipe? You leave the hose hooked up on your house, right? And it bursts the pipe in the basement or crawl space, right? The crack is along the length of the pipe. That's because the stresses around the hoop, what we call hoop stresses, or stresses around the perimeter of the pipe, are twice that of the stresses that are along the length of the pipe. And so it's always gonna burst and crack, you know, the tear is gonna be along the length because it's gonna wanna burst radially and not along the length. Pretty cool, right? So now you guys wanna get to pressure vessels, huh? So then in that case, you would have a hoop stress potentially. If this was a pipe and it had pressure in it, then you could have a sigma y, for sure, definitely. So we got Moore's circle. We need to plot our points. Well, we know that our shear stress is plotted on our y-axis, normal stress on our x-axis. We know that the bottom, because it's positive, right-hand rule, I usually just twist my fingers in the direction of the arrow. I want my thumb pointing out of the page is positive, so it's counterclockwise. And then if we're above, we're clockwise. Okay. Well, if we look at this stress block, right, we have 2 points to plot on this Morse circle, right, or plot. We have our coordinates on the x face and coordinate on the y face. Well, if we start with the x face, right, we have a 95.5 megapascal tension stress, and then we have a shear stress of 63.7 megapascals, right? That shear stress on our x face is twisting our block clockwise. Well, if it's twisting our block clockwise, that means we're going to be up here, right? So we're going to be over here, and we're going to be up here. We're going to be in the first quadrant, right? So I'm just going to guess. I'm just going to throw something out here. I'm going to say that it's somewhere around there, 95. So we've got sigma x comma tau xy. That's our coordinate. That's 95.5 comma 63.7. Right? That's the coordinates of that point out there. It doesn't really look like a 9, does it? 95.5. Similarly, well, now we plot what's going on the y face. Well, we have 0 normal stress, right? So we're going to be along this y-axis. But we have, similarly, we have a shear stress, same magnitude, but now it's trying to twist our block in the opposite direction. Or counterclockwise, so we're below the x-axis, an equal amount. So if we're up there, we're going to be somewhere down here, and we're on the y-axis. So where our point we're going to plot is somewhere right about there. This is sigma y comma tau yx, right? That's the shear stress on the y face in the x direction. Our actual coordinates are 0 comma 63.7. I like to connect these with a line. That line gives us this center point, right? Where we cross the x-axis. That's going to be our center of our circle. If we draw a beautiful circle like that, damn, that's good. Huh? Dare you to copy that shit. All right. We've got this beautiful circle now, right? We know 2 points on the circle. We know the center of the circle, right? We know that we're going to have a radius. This is where you could just visualize this, right? And say, okay, I know this is 95.5. I know this is 0. Well, this is going to be the average of that. So it's in the middle. Because of that, then I know the x component of this triangle. The y component is just 63.7. I can get the radius. Right? All of those things, you just kind of work through the geometry of our circle to figure out what the hell's going on. Right? So if we work through the equations, the center, right, or sigma average, sigma x plus sigma y over 0, or sorry, not over 0, that's not right, over 2, well, we get 47.25 megapascals. Radius, square root, sigma x minus sigma y over 2 squared plus tau xy squared. Plugging everything in, we get 79.6 megapascals for our radius, right? Which makes sense. 42.25, well, that's just really half of 95.5. Right, we started at 0, we're going to 95.5, well, that's going to be the center, right, with respect to the x coordinate, y coordinate, or sorry, the radius. Well, now we know what the components of the triangle would be. Square root of the sum of the squares, we get the hypotenuse, that's the radius. And we've created our Moore's circle, and we know now some of the critical components of that Moore's circle, the center and the radius, right? So what did they ask us for? They asked us for, got 4 minutes here, they asked us for a couple things. They asked us for what's the maximum shear stress and what are our principal stresses. Well, what does that mean? Where are our principal stresses? Give me something.
How it's
They're on our axis, right? The x-axis. Yep. So we're these 2 points here. This is sigma 1. This is sigma 2. Right? Our maximum shear stress is top and bottom of the circle, right? So we have our tau max. Well, that's pretty easy to figure out now. If we know the center, we can figure out sigma 1 and sigma 2. It's just the center plus the radius and the center minus the radius. Okay? Tau max, well, that's really simple. It's just the radius, right? It's always just going to be the radius. So we have sigma max, which is sigma 1, is the center plus the radius. That's 159.2 megapascals. Sigma min, well, that's sigma 2. That's the center minus the radius. Well, look at here. We've got ourselves some compression going on. All right, things are getting exciting. So we have sigma max, sigma 1, sigma min, sigma 2. If we wanted to know now, right, we have this stress block. It's oriented along the length of this shaft. If we wanted to know, well, what is the angle with which we would need to cut this shaft in order to see the maximum stresses? That's this angle right here, right? If we took the x face, we would need to rotate clockwise, that angle, alpha, in order to move sigma x to sigma 1. Right? And similarly, if we move that alpha, sigma x goes to sigma 1, and sigma y goes to sigma 2. Right? How do we figure that out? Well, we figure out the opposite and the adjacent sides. Right? That would give us that angle. Well, if we did the tangent, inverse tangent, opposite over adjacent equals alpha, right? That is tangent, -1. Well, our opposite is really 63.7 megapascals. Our adjacent is going to be our 95.5 minus the center, 47.25, or really just the radius. Or sorry, what's that? Yes, that's right. Equals 52.8 degrees. Well, that's alpha, right? And if we want theta, theta equals alpha over 2, or 26.4 degrees. So if we wanted to see or know an orientation that gave us our maximum stresses, our maximum normal stresses, we would need to look at a plane that's rotated 26.4 degrees. And we'll finish this example on Monday. Have a great break. Don't forget there's a quiz. If you haven't started it yet, it's due by the end of the day, okay? Don't forget that, all right? Be safe when you're out there this week, okay? Have fun.